Welcome to my first video on vehicle electrical systems. This is an introductory video, and this video contains mostly theory, but we will get into a lot more practical application in following videos. Hopefully you can take something from these videos, and if you're afraid of electrical, hopefully you won't be. To start off, let's just talk about what an electron is. That's kind of the basis of what electrical is the transfer of electrons. To understand what an electron is, we need to understand the basic principles of what's contained within an atom. In an atom, as you can see in my drawing here, we have a nucleus, and in this nucleus, we have protons and neutrons. I drew them in different colors so it's easier to understand. The amount of protons defines what element you're dealing with. For example, let's say you have 29 protons in the center here. That would be copper. Atomic number is 29, which would mean it has 29 protons. If we change the amount of protons, let's say it's 28 protons, now we have nickel. Protons are positively charged. Neutrons, they're neutral. They don't really play a role in um, electrical charge in an atom. Electrons are not contained within the nucleus. You can see them orbiting around here in different shells or different bands, and they're negatively charged. If we have equal amount of electrons for equal amount of protons, it's a neutral balance. If we have more electrons than protons, then it's negatively charged and it's called an anion. If it has less electrons than protons, called a cation and is positively charged. The most important thing here that we need to know is what is a valence shell. The valence shell is the very outmost shell. You can see here on this copper atom, we have this one solely little guy sitting by himself on this outside shell. That guy is what determines the reactivity of copper. Copper is a great conductor. Everyone knows that copper is used for wires all the time. This one little guy does most of the work. I do want to also point out how many electrons are held in each band. The first band can only hold a maximum of 2 electrons. Second band can hold a maximum of 8 electrons. Third band can hold a maximum of 18 electrons, so on and so forth. And the amount of electrons in the valence shell determines if it's a good conductor, if it's a semiconductor, or if it's an insulator. I'll get more into that later, but the formula for figuring out how many electrons you can hold within a valence shell is 2n squared, n being the number of valence shell it is. The closest one is the first shell, second one's the second shell, third one's the third shell. So third shell, 2, third shell would be n3. So it'd be 3 to the power of 2 is 9 times 2 is 18. So it's 18 electrons in that shell, maximum. Now, the thing about valence shells is they always want to be stable, which means if they have a small amount, for example, this valence shell only has one, it kind of wants to lose that. It wants to get rid of that electron so it can have a stable 18 electron valence shell. Very stable. Now, when we get to insulators, they have a lot of electrons on that valence shell, and they'll take electrons in, and they don't want to get rid of those electrons because they're more stable the more electrons they have. The fuller the shell, the more stable it is. The less there is, it's easier to just get rid of one than it is to get rid of 9. Now let's talk about insulators, conductors, and semiconductors. Insulators are materials that inhibit electricity flow. Common examples of insulators are rubber. You can see that on tires. They have the saying that if electricity, such as lightning, hits your car, you're supposed to stay within your car because the only thing that's preventing you from getting shocked is the rubber wheels that you have. Then we have plastics. Great example, fence posts. Electric fences, they use wood. Wood is a good insulator, and they use plastic clips to hold that electrical wire. Another good insulator is hydrocarbons, which is like oils and fuels. A lot of times we have injector wiring that goes to the top of our engines, always covered in oil. Think about how, if oils were a good conductor, why would we have wiring going through our engine heads? That wouldn't make sense. Usually, a factor indicating it's an insulator is that it will have more than 4 valence electrons. As I was saying earlier, the more electrons it has, the more stable it is. The fuller the valence shell, the more stable it is. So if it has more than 4 valence electrons, it'll take electrons from other elements beside it, but it's not going to want to get rid of those electrons that it has. Moving on to conductors, there's several materials which are good conductors. Conductors allow electricity to flow through them with ease. Not all are equal, but examples of conductors are silver, copper, gold, aluminum, steel, and cast iron. This is in order of most conductive to least conductive, but we don't really see a lot of these metals used in things like wiring or pretty much any application. The pretty much the only things we see is steel, copper, and gold. And the reason why we don't use silver, although it's the best conductor we have, it corrodes rapidly. Copper, it has relatively low resistance. It's pretty cheap and it's pretty resistant to corrosion and it's pretty flexible. Gold, on the other hand, has higher resistance than copper, but is often used to plate contacts. You'll see that usually in ECMs or motherboards or any sort of electrical components, computers. They always use gold for good contacts. Gold is super soft. You can have a super good contact with it, but it does have higher resistance than copper. And aluminum is pretty cheap, but aluminum corrodes pretty fast. You can see that with most aluminum products. You got that white dust that builds up on top of it, and it's not flexible. You can see that a lot when you try to flex aluminum, aluminum will more easily break than flex. Tungsten, yeah, you see it often in light bulb filaments. It's decently priced. Uh, it has an acceptable amount of service life to it. And steel and cast iron, the only reason why steel and cast iron is on this, it's not that good of a conductor, but we use it for ground circuits all the time. Steel, because we have such a big piece of steel, your whole engine is steel, your whole frame is steel. You have such a wide area, the amount of resistance you're actually having because of how large it is minimal. So that's why we use things like steel for ground circuits. You'll find like a bunch of eyelets on your vehicle just going straight to any sort of steel piece. Your hood, you'll find a ground off your hood itself because your hood is made out of steel. One thing to note with conductors is conductors have less than 4 valence electrons. Now, semiconductors, examples of semiconductors are silicon, germanium, carbon. They have 4 valence electrons, and they can act as both a conductor or an insulator depending on which properties that you give them. They are not as good as a conductor as a normal conductor, but they will conduct current given the right properties. One thing I want to mention is carbon pile testers. A lot of times you don't really think about it when you're testing equipment. How is it that you can have something where you can vary the amount of load or resistance you're putting on a circuit? What's happening with that? What's inside a carbon pile tester are these carbon plates, and carbon is something very unique, where the more compression you put under carbon, the better it acts as a conductor. Under atmospheric pressure, carbon is not a good conductor. So the way a carbon pile tester works is it changes the compression on carbon plates to vary the amount of current you want flowing through. It varies the amount of compression. Now I want to get into voltage, amperage, and resistance. Um, when we get into things like voltage, let's talk about voltage first. It is, in my opinion, the best way to describe voltage is a potential difference. Sometimes you'll have other references. Sometimes they'll call it, instead of saying voltage, they'll call it something like electromotive force. Too fancy for what we're dealing with. We could just call it voltage, call it potential difference. Doesn't really matter. There are many sources of voltage. We see electrostatic here. Think of the way a balloon works. You create a electrostatic voltage when you rub that balloon on the top of your head. Electrons are stripped from your head and end up on that balloon. That balloon is now sitting at a negative charge, and it'll stick to things like flat surfaces like walls. Uh, and the opposite charges attract, the balloon will stay because of all the positive end regions of that wall will come to the end of the wall, and the negative charge regions of the balloon will end up on that one side of the balloon close to the wall. And it's called a van der Waals interaction. You don't need to worry about that. But just know that with the static electricity, it can cause a lot of damage. Electrostatic shocks that produce light are thousands of volts. If you think about your standard car battery, it's 12 volts. How come an electric shock doesn't do a lot of damage? That's because the amount of current flowing through that electric shock is minimal, but it's at a very high voltage. Although it doesn't affect the human body, it sure can affect electrical components. Because it can damage electrical components, we wear things like ground straps. Usually it's like a bracelet that goes around your wrist. You can see on this drawing of a hand, I have this bracelet that went around the wrist. It has a little alligator clip. And you wear this when you're dealing with things like ECMs or computers because you do not want that thousands of volts going through that computer. Even if you don't think it's damaged, it can be damaged. You notice it 10 years down the line, 4 years down the line, maybe a year down the line, or it could be instantaneous damage. It varies. Now talking about electrochemical. Electrochemical voltage is electrical potential created with certain chemicals, lead and sulfuric acid, inside our standard lead acid battery. I'll get more into this in a different video. I feel like batteries have their own separate topic. And electromagnetic induction, you can see here with this circle wheel of magnets. This is kind of like how your alternator works. I'm going to get into alternators and electromagnetic induction into another video. It's kind of these are very large topics and they can't be covered within this video. And we also have this piezoelectric quartz here. Piezoelectric it's very interesting. Most common piezo is quartz, and you need a specific crystalline structure for it to work. It's not going to work with your standard kitchen countertop. When quartz is compressed, it causes the tiny quartz crystals to be unbalanced, adding a voltage potential on each side. It's a very small voltage, but also keep in mind that if you do the exact opposite, instead of compressing it, but you apply voltage to the crystal, it'll expand. Applications where you see piezoelectric crystals is they started implementing them into roads to know when somebody's at a red light. They use them for sidewalks for knowing how many people are sitting at a sidewalk. You use them for knock sensors, and you also see them in certain injectors as well. As far as creating voltage with heat, when you have two dissimilar metals and you heat it up, you can create a voltage difference. It's used for certain sensors. I'm not going to get too much into it. I don't think it matters that much. And now let's talk about amperage. Amperage is defined as how many electrons are flowing through a given point in 1 second. 1 ampere is equal to 6.28 times 10 to the power of 18 electrons, which is equivalent to 6.28 billion electrons passing a point in the conductor in 1 second. So that's like this one tiny little band here. That's how many electrons are flowing in 1 second. I drew this picture. I think water symbolizes voltage and amperage and resistance pretty well. When you have things like a water tower, for instance, the potential voltage is the amount of water you have inside that water tower. Amperage is the amount of water flowing through that pipe from that water tower. Now, when we talk about electrons passing, electrons flowing, we're talking about flow here. Which direction does it flow? We have batteries, we have a positive terminal and a negative terminal. Which way does current flow? Both are technically right. I would say that one is more right, but both are used. When we're talking about electron transfer, we're talking about a negative charge transferring to a positive charge. We're talking about electron flow. They're inherently negative. With electron theory, electricity flows from negative to positive. Conventional theory is a little bit older than electron theory. It's not more right, but it's older. So they say that the absence of electrons flow from positive to negative. That doesn't make sense because having nothing flow from positive to negative is basically what they're saying. But All our wiring diagrams, all our circuits, our pictograms, everything's written in conventional theory. So that's the way I'm going to continue forward, is using conventional theory. Resistance. Resistance. We have multiple things that affect resistance. It's basically just as it sounds. Resistance is a restriction to flow. Now back to this water tower example. We have this little blockage in here. We have the same amount of potential volts, right? Same amount of water, but now we have this restriction in this line, and throughout the rest of the line, you see this air that sits above there, so that your amperage is basically cut in half with this restriction. And that's how resistance kind of affects a circuit. So you still have your voltage, but you see as resistance increases, amperage decreases. The unit for measuring resistance is the ohm. It's used with the symbol of the omega. Now let's talk about which factors affect resistance. Well, there's many things that affect resistance. We got wire size. Size will affect resistance, and it's inversely proportional. So as size increases, resistance goes down. That's why when we have things like starter cables, they're so large because we need a lot of amperage getting to that starter. We need a lot of power to start our engine, therefore we need larger starter cables. Length also plays a factor. As there isn't material with perfect energy transfer, you'll always have a little bit of resistance in any material you use. The longer the path, the more you're going through that resistance in that wire, which means at the end of it, you're going to have a lot more resistance. Now, the way power lines limit the energy lost through its wires is by transferring it at very high voltage. So when we talk about amperage, we're talking about current flow, how much is actually flowing through it. What high voltage power lines do is they limit the amperage to almost nothing, but have really, really, really high voltage, up to 380,000 volts being transferred. And then they have what's called a step down transformer. It limits the voltage to a reasonable level, increases the amperage, and then we have our 120 volt house plug. I'm going to make types of materials brief. We already talked about types of materials earlier. I just want to add one thing, and it's talking about solder. If you ask one person, they'll say solder is good. Ask another person, they'll say solder is bad. In my opinion and my experience, it depends on application and if it's done right. The problem with solder is tin binding is not good with vibration, and it'll tend to break on wires that see a lot of movement. I would advise butt connectors, as you can see here in this picture, these little metal tin butt connectors. I would advise butt connectors on most of your applications, but when it comes down to if solder is actually bad, I wouldn't say solder is bad. Another problem with solder is the person using it. Using acid core solder is only for plumbing and metalwork. It has no place for wiring as it causes copper deterioration. Another thing to keep in mind, if you overheat copper, it oxidizes. When copper gets oxidized, it corrodes. So if you're using solder, be careful not to overheat the copper. And please, please always use shrink tube. How many times I've dealt with people using electrical tape to cover up wires is unbearable. It doesn't prevent moisture from getting in, it just causes a headache. Let's talk about temperature. Temperature plays an interesting role in electrical systems. When temperature increases in a standard conductor such as copper, resistance increases as well. This is due to an increase of collision rate between flowing electrons. The excited atoms of the copper impede current flow. This is referred to as a positive temperature coefficient reaction. A semiconductor, on the other hand, is a negative temperature coefficient device, meaning as temperature increases, resistance actually decreases. This is because extra temperature gives energy to the valence electrons, allowing them to more readily jump out of their valence band. Keep in mind, temperature sensors, such as a coolant temperature sensor, could be either or. It could be a positive temperature coefficient, copper inside, or it could be a negative temperature coefficient, where it has a semiconductor inside. So be careful when testing temperature sensors and knowing which one is which. Types of current. There are two types of current we'll see, DC and AC. DC stands for direct current, AC stands for alternating current. DC is something you'll see like in your battery. It only flows one way. It's like the water tower example. You have that large sum of water and gravity pushes it one direction. Now, with AC, it's a little bit different. Alternating current flows both ways. It's like a tide or a wave hitting a shore. It'll flow towards the beach and it'll flow backwards. For standard applications, we always want to use DC. Our household appliances convert AC voltage to DC voltage. But for transferring and transformers, we need AC voltage. So when we're using really high voltage transfer, like those power wires we talked about earlier, we need transformers because we're using electromagnetic induction, which we'll talk about in a different video. And that's the increase and collapsing of magnetic fields. And the only way we can do that is by switching directions very fast. I would just want to point out alternators produce AC current, but convert it to DC before it actually leaves the alternator. Let's talk about the Ohm's law triangle or the voltage triangle now that we talked about voltage, amperage, and resistance. The voltage triangle or Ohm's law triangle is a representation of the relationship voltage, current, and resistance have. The way the triangle works is if you don't have one of these values, you can solve for it using the other two values. Keep in mind, you can see how resistance and amperage are inversely proportional. We've seen that with the water tower example when I was showing the restriction causing the amperage to be cut in half. If you have a given 12 volts on a battery and resistance goes up, amperage will have to go down. Let's try a couple triangle calculations. As you can see here on the triangle, if we have 12 volts at 2 amps, we'll have 6 ohms of resistance. 2 times 6 is 12. 12 divided by 6 is 2. 12 divided by 2 is 6. Okay, so now that you've seen the relation of the triangle, let's do some of these calculations. We've got 12 volts at 4 amps. So we go 12 divided by 4 would give us 3 ohms. Let's look at this one. So we have an amperage of 4, and we have 4 ohms of resistance. And we're solving for voltage. Because it's on the top of the triangle, we'll have to multiply the bottom too. We'd go 4 multiplied by 4, which would give us 16 volts. Now for this one, it's pretty much the same as this one, just solve for a different value. Solve this one, you'd have 14 volts divided by 1 ohm, give us 14 amps. Thank you guys for watching this video. This is just the first part of my video series. I'm going to go a lot more into practicality in further videos, but I think it's important to understand the theory and the basics of it before proceeding further. Otherwise, if you build your foundation with a weak base, it'll just cause you more struggle later on. Thank you for watching this video.